Hey guys, in this video what we're going to look at is something called trigonometric substitution. In your textbook it corresponds with section 8.4. So this information that I have on this slide is on page 554, so if you could open your book to that page that would be great. And so let's see here. What we're going to be looking at, the types of problems we're going to use this for is when you see integrals involving radicals like these. So if you have a squared minus u squared and under a square root sign, or a squared plus u squared, or u squared minus a squared. And basically a is going to be a number, the u is going to be a variable for these. The objective with trig substitution is to eliminate the radical in the integrand. And so what we're going to do is we're going to use Pythagorean identities, which we have the way that we first learned it was sine squared x plus cosine squared x equals 1, but you can rearrange it and you can use any variable. So cosine squared theta is equal to 1 minus sine squared theta. That's one Pythagorean identity. This is another. Secant squared theta equals 1 plus tangent squared theta. And tangent squared theta equals secant squared theta minus 1. All right, so let's just look at how this is going to work. If you let u equal sine of theta, and I'll show you how this works with a triangle in just a minute. If you let u equal sine of theta, then we can replace u, because u is equal to a sine of theta, we can replace this u here with a sine of theta, but we have to square it because it's u squared. So you get a squared minus a squared times sine squared theta, and it's all under a radical. I can factor out an a squared, and what's left inside the parentheses is 1 minus sine squared theta. That is equivalent to cosine squared theta in that identity. So we have the square root of a squared cosine squared theta. Since this is now a product instead of subtraction or a difference, we can take the square root of a and we can take the square root of cosine, and we end up with the square root of a squared minus u squared. We can use a trig substitution, a cosine of theta. And you'll see how this works when we do some examples. So let's just review the Pythagorean theorem, because that's where all this is going to come from. If you have a right triangle and the hypotenuse is c, then by the Pythagorean theorem, a squared plus b squared is equal to c squared. And if you solve that for c by taking the square root of both sides, you get c equals a squared plus b squared. So a and b, with addition here, those are the legs of the triangle, and c is the hypotenuse. Or if you have a leg here squared, if I solve this Pythagorean theorem for a squared by subtracting b squared and solve it for a, you end up with the square root of c squared, which is the hypotenuse squared, minus the other leg squared. So if you see subtraction, you're going to be thinking that this first term is going to be the hypotenuse when you relate this to the right triangle. And same thing for b equals the square root of c squared minus a squared. The c would be the hypotenuse. Okay, so this, also on page 554, I gotta move my picture out of the way here. This is the trig substitution that you're going to use. So you're going to probably want to reference this page, or we can summarize it even shorter in a second here. But here we have a right triangle, and for integrals that involve a squared minus u squared, a would be the hypotenuse and u would be one of the legs. And if this is theta here, we can write this as sine of theta. Come on, move out of the way. Sine theta is equal to u. Okay, hold on a second. Let me move this picture. So here, if we have, if this is our reference angle, and we take the sine of that reference angle, it's equal to the opposite, which is u, divided by the hypotenuse, which is my a over here. Solving that for u, we end up with u equals a sine of theta. So if you see the square root of u squared minus, the square root write this down. If you see the square root of a squared minus u squared, you're going to replace that. We're going to, your u, oops, let me write that a little bit differently. You can replace this with, hang on, our u is equal to a sine of theta from that triangle, and if we replace u with a sine of theta and square that, we get a squared times sine of squared theta, and then that becomes, so this is not equal to, move that over here, that becomes, we can factor out an a squared, and I'm left with 1 minus sine squared theta, and this is what I had just done. But then we have the square root of, or yeah, a squared, and then 1 minus sine squared theta is cosine squared theta, and so this a squared minus u squared, square root of that, is equal to a cosine of theta. We're going to use that substitution as well. All right, so the next one, so that's number 1. The next one, when you have a plus sign, a squared plus u squared, those are going to be my legs, and I have a here and u here, and if this is theta, the trig function that involves those two legs is the tangent. So the tangent, let me do my color here, the tangent of the angle is opposite over adjacent. Solving that, if we solve that for u by multiplying both sides by a, I get u is equal to a tan of theta. All right, so if it's a squared plus u squared, it's the u is equal to a tan of theta. So u would equal, oops, a tan of theta. And replacing u up here with a tan of theta, you're going to end up with a squared plus u squared, which is a tan of theta squared, so square the a, square the tangent. If we factor out an a squared, you're left with 1 plus tangent squared theta, and by the Pythagorean identity, that 1 plus tangent squared theta is secant squared theta, which, taking the square root of both because it's a product, you can do that. This original a squared plus u squared can be substituted with a secant of theta. Okay, then the third one here is for integrals involving u squared minus a squared, where u is now the hypotenuse. You have, and a is a leg, so if this is u and this is a, then the side opposite here would be the square root of u squared minus a squared. You can use the Pythagorean theorem to figure that out. And if you take the secant of theta, secant theta is equal to the hypotenuse over the side adjacent. Solving that for u, you end up with u is equal to a secant of theta. So when you have the square root of u squared minus a squared, the u is a secant of theta. And then let's throw that in here in place of u. So I have a secant theta, and then again that's squared, so a squared secant theta squared minus a squared. Factor out that a squared times secant squared theta minus 1. Look at your trig identities. The u squared minus a squared can be replaced with, oops, this let me do one more step here. Secant squared theta minus 1 is equivalent to tangent squared theta by the Pythagorean identities. So you're going to use this substitution, a tangent of theta, when you see the square root of u squared minus a squared. So this is an intro of what the substitution values will be, and then in the next video we will do some examples on how to use this.